Chapter 16 is about solubility and complex ion equilibria. In this first section, we will be looking at the equilibrium associated with solids dissolving to form aqueous solutions. We'll be introduced to something called the KSP, and we can use that to determine solubility. KSP is the solubility product or solubility product constant. It is an equilibrium constant, therefore it has only one value at a given temperature, and if the temperature changes, that value will change. If we look at the equation below, we see a solid dissolving to give us an aqueous solution of ions. And according to the law of mass action, we can see what the equilibrium expression would be. No solids are included, only the concentrations of the ions. This equilibrium system represents a saturated aqueous solution. As the dissolution proceeds, it is likely that the ions will bump back into each other to reform the solid, so that is why it is a reversible reaction. However, the solubility of this saturated aqueous solution is different than the solubility product constant. The solubility is an equilibrium position, so in pure water for a given substance there will be one solubility, and then if there is a common ion, that will represent a different solubility. However, the KSP will always remain the same as long as the temperature is constant. Here are the KSP values for some common ionic solids. This is on page 761 of your textbook. You'll notice most of these would be considered insoluble according to the solubility rules that we learned earlier. We cannot just compare KSP values to tell us something about the solubility like we did with, say, Ka values for acids. In order to compare KSP values directly, the salts have to contain the same number of ions. For example, if you had a binary salt, say like silver iodide or copper iodide, we would calculate the KSP by taking the concentration of the cation times the concentration of the anion. And for something like silver iodide, those would be the same value. So you could say S squared, where S is our solubility in moles per liter. To compare the KSP values for salts directly, if all the salts are calculated in this same way, we can compare them. They produce the same number of ions. However, if the salts contain different numbers of ions, then you would want to go back and calculate the solubility first and then just compare those solubilities. We'll talk about how to calculate solubilities in a moment, but just take a look at the KSP values for these three salts, and then take a look at the calculated solubilities. If we just looked at KSPs, we would predict that this one is the least soluble. However, if we look at the solubilities, we actually see this one is the least soluble. And that's because these compounds have different numbers of ions. Here we have a 1-to-1 ratio in our ions, a 2-to-1 ratio, and a 2-to-3 ratio for our ions. So we cannot compare KSP values directly if we have different numbers of ions in our salts. So this is not true. Okay, so let's talk about how to actually calculate the solubilities. We're going to do silver chloride first. We get silver ions and chloride ions when silver chloride is dissolved in water. Our equilibrium expression looks like this. To find the solubility, we must find the equilibrium concentrations of the silver ion and the chloride ion. We can use the KSP and set that equal to x times x, or x squared. For every one silver ion, there is one chloride ion, and we assume that initially there were no ions in the solution. So at equilibrium, the concentration of silver ion is x, as is the concentration of the chloride ion. If we go through and solve, we get 1.3 times 10 to the negative fifth molar. We do need units on this since we are solving for a concentration and therefore solubility. Now, if we didn't want the solubility in moles per liter, it could be converted to, say, grams per liter, or grams per 100 grams of water are some other units that you might typically see for solubility. Now let's calculate the solubility for silver phosphate in water. KSP is 1.8 times 10 to the negative 18th. So here's our chemical equation up here at the top. We get 3 silver ions for every 1 phosphate ion. Our equilibrium expression shows that the KSP is equal to the silver ion concentration cubed times the phosphate ion concentration. And since we get 3 times the amount of silver ions as phosphate ions, I'm going to call the concentration of the silver ion 3x and the concentration of the phosphate ion x. Now the quantity 3x does need to be cubed. And if I simplify the right side, I get 27x to the fourth. If I go through and solve for x, 1.6 times 10 to the negative fifth molar is my answer. This is the solubility because the phosphate ion and the silver phosphate are in a 1-to-1 ratio. Now let's calculate the KSP given the solubility. So I have the equation for our bismuth sulfide here and our equilibrium expression. Notice that the concentration of the bismuth ion is squared and the sulfide ion is cubed. Based on stoichiometry, the concentration of the bismuth ion is 2 times 1 times 10 to the negative 15th. So 2 times 10 to the negative 15th, and that quantity is squared. And the concentration of the sulfide ion is 3 times 1 times 10 to the negative 15th, or 3 times 10 to the negative 15th, and that quantity is cubed. So our coefficients are used in 2 ways here, stoichiometry and then based on the equilibrium expression. We get 1.1 times 10 to the negative 73rd, and yes, this is a very tiny number. Now let's talk about if we have a common ion. The solubility of a solid is going to be lowered if the solution already contains ions that are common to the solid. For example, we're going to look at silver chloride in calcium chloride, and here we have this common ion, chloride. According to Le Chatelier's principle, if we have chloride ion, the reaction will shift left, and that will reduce our solubility. Here's our equilibrium expression. Normally we would put in X for the silver ion concentration and X for the chloride ion concentration, but we already have a common ion, chloride. So the concentration of the chloride ion becomes 8 times 10 to the negative third plus X. However, I can simplify this since the KSP is so small and get rid of this term. Now you might be wondering, where did the 8 times 10 to the negative third come from? Well, the concentration of the calcium chloride is 4 times 10 to the negative third, and the formula for calcium chloride is CaCl2, so there are 2 chloride ions for every 1 calcium ion. If I go through and I solve for X, I get 2 times 10 to the negative 8th molar. I can check this value with the 5% rule to make sure that it was okay to make this assumption right here. And it is according to the 5% rule. So here is our solubility. And as a side note, the solubility of silver chloride in just water is 1.3 times 10 to the negative 5th molar. So you can see that the solubility has decreased with the addition of a common ion. And finally, let's talk about the effect of solubility with pH. If the anion in your salt, we're going to call that X minus, is an effective base, meaning it came from a weak acid, HX, so there's your acidic hydrogen there. The salt that's made of X, so we're going to call this MX, is going to show an increased solubility in acidic solution. So here's our salt MX, and you can see it dissociated. Hydrogen ions in an acidic solution will react with the anion and actually pull it out of solution. As a result, the reaction will shift right and increase the solubility. Some of the ions that we would probably be looking for are right here. For example, hydrogen ion would react with sulfide ion to make this or this. So let's end with, how does the solubility of silver phosphate in water compare to that of silver phosphate in an acidic solution made by adding nitric acid to the solution? So here's our dissociation equation. And nitric acid contains hydrogen ion, which can react with this phosphate ion. Phosphoric acid is a weak acid. And so then this reaction would shift to the right to replace the missing phosphate ion. And then that means that the silver phosphate in the acidic solution is more soluble. Now for this question, how does the KSP of silver phosphate in water compare to that of silver phosphate in an acidic solution made by adding nitric acid to the solution? Because it's a KSP and because no temperature change is mentioned, it should be the same. So we're talking about different equilibrium positions when we're talking about changes in solubility, but this equilibrium constant, this KSP, should remain the same unless the temperature is changed.